Okay. All right. Well, happy Monday. Hope you guys are doing well. Week 5, so midterms and all of that's going on. All right. This week we are, well, at least in today's lecture, we'll take a look at optimizing a model, but this time from a maximum likelihood perspective. So, in the first part of our course, we talked about optimization, but it was from a loss minimization perspective. So we were fitting our models by trying to minimize a loss function, also called a cost function. And it would be things like we are trying to minimize the total squared errors. And that was a versatile cost function. It works for all, any kind of regression or, numeric prediction context. So for linear regression, we work to minimize the sum of squared errors. Even in neural networks, when we are trying to predict a numeric output or even a categorical output, we converted our categorical output, our labels of digits, handwritten digits, into zeros and ones, and we said we want to minimize the sum of squared errors. Okay, and so it's a very versatile function, and a lot of machine learning methods rely on that as a way to train our models. Okay. What we want to take a look at today is training our models from a maximization perspective. And so this time we are going to maximize a different function. And so rather than trying to minimize the cost function, we're going to try to maximize the likelihood of our data. And that's what we'll take a look at. Again, we're going to start off in the context of least squares regression. This is a context that we are very familiar with, and so these ideas of, what is it that we're trying to optimize, I hope is familiar. So, as far as least squares regression, we set up a linear model, and our linear model, has some predictors in our X matrix. And we have a set of weights or coefficients, and here we call them W. But in traditional linear regression textbooks, there often are betas, but it's the same idea. We just call them W. These are our weights, and a linear combination would be to multiply each of our weights by each of our X predictors, and then we combine them and add them up. And so our predicted values are T hats, or predicted of the target values, will be our weights times our vector of X values for the nth observation. That's how we get our nth prediction T. Okay, and so the way we tried to figure out our W's is to find the W, the value of W that minimizes our mean squared errors, and the mean squared errors can be written this way. For each observation n, we take the difference between the actual value of t for the nth observation and our predicted value for t. Take that difference, we square them and add them up, and that can be written in kind of matrix notation by doing t minus xw transpose t minus xw, which is exactly equivalent to this. And this is our mean squared error, and we said, the way we're going to figure out our w's is find the w that's going to minimize this expression, and that was what we did. Okay, the approach that was used to train a linear regression model is the same approach we used for training a neural network. We defined a way for our model to make predictions based on inputs x and model parameters w. For linear regression, it's just w times x. For neural networks, the forward feed process is a little bit more complicated, but at its core, we have a model that makes predictions based on input x and model parameters w. we've defined a loss, which was our mean squared error, and we said we're going to minimize this loss function to figure out our W's. We also had a modification of the loss function when we did regularized least squares. We said, for regularized least squares, we're trying to minimize the loss function along with the complexity parameter, right? So that was another approach, okay? And what we are going to do today is, rather than minimizing the loss, we're going to try to maximize the likelihood of our data. And so maximizing the likelihood requires us to have what we call a generative model, a model that says this is the random process that generates our data. And so we're going to kind of review some elements of maximum likelihood estimation, because our goal is going to be to maximize the likelihood, okay? And so when we talk about a generative model, we say the data that we have, our observed data, is the result of a process that includes a random element. Usually that random element will be random noise. And so for linear regression, our generative model looks like this. We say, any observation you actually have, so these are actual observations, is basically going to be the part that we are predicting, the W times the X, okay, plus random noise, okay, plus some epsilon. And, and this, it looks, very, very similar to what we had before. We said, earlier we said W transpose X sub n gives us our predicted value, our nth observation, our nth predicted value, T hat sub n. And the only real difference is that we are saying Tn, okay, the actual value of T, the nth value of T, is basically the predicted component T hat, sorry, there should be a subscript n here, T hat's our nth T hat plus our epsilon, okay? And so we're just, in our key here, we say the actual value is just our model prediction plus random error, okay? So we still have a model, and we just have a way to link our model to the actual value by saying there is a random error component. This was not, and you feel like, well, isn't this what we've always been doing? And the answer is no. When we were back here, okay, we didn't have any kind of random noise modeled in here. We just said, this is how we're predicting it, and our goal is to minimize this function, okay, is to minimize the difference between the actual values and our predictions. And we didn't model any kind of random noise. Now, whenever you take linear regression 101A and then also your linear models class 100C, this random error is an integral part. And so it feels like, oh, I thought this was always kind of part of it. But as far as neural networks go, we never talked about random noise or randomness. It was just, this is how we get our predictions. These are the actual values, and our goal is just strictly to get our predictions as close to the actual values as possible. And therefore, because we're not modeling any kind of random noise, there's no real assumptions that we have to check. Whenever you do, say, linear regression, and you have a linear model and you are including the random error, we have assumptions about the distribution from which epsilon sub n comes from, and you have to kind of verify that those assumptions haven't been violated. But with the neural network, we don't really care. There's no randomness, there's no assumptions about the error, because the error is not factored in at all. As far as training, we just say, hey, find the W's that give us the best performance here, and that's it, okay? But here we have a generative model, and the generative model includes random noise. All right, and so this inclusion of random noise makes our model probabilistic. And so by including the random noise, we have a probabilistic model. And so our observations can now be said to come from some kind of distribution. And whenever you have a distribution, you can then calculate the likelihood of the data that you've observed. And so now our goal is a little bit different, and we are going to try to find the model parameters that will maximize the likelihood of our data. Okay, so we're going to try to find, what set of W's are going to maximize the likelihood of our data. And so here is our linear model, and we are going to make the assumption, okay, and we're going to model our random error as coming from a normal distribution where the mean is 0 and the variance is constant, and we're going to put in a sigma squared there. And if we combine this and we say, all right, our predicted values T sub n is this, it's basically, we're putting this part in, and because the mean is at 0, we can just say, all right, our observed values of T come from a normal model where the mean is now our predicted value, and we have noise, random noise, with variance sigma squared. Okay, let me go ahead and give you your first view quiz answer, which is the letter E. E as an elephant. E. Okay. All right, and so here's just a plot of, just some dots here, and the idea is we're going to fit a model, okay? And so our fitted line might look like this, and the idea here is at any kind of value x that we can plug in, our regression line, our predictions will be centered at that regression line, and you can imagine a normal distribution that is centered at this at the prediction, and therefore the actual values that we observe, we expect most of them to be kind of close to the regression line, but there's random noise, and this is what we have. And so, any kind of value that we actually have, we have a distribution centered there, and this is how we expect our the observed values to be generated there. Okay. All right, and so every observation now has a probabilistic expression, and what we are going to do is we're going to try to select our model parameters so that we are maximizing the likelihood of the data that we have. Okay. What's the difference between likelihood and probability? Pop quiz. So at its core, they're very similar. The key difference is that probabilities, if you say integrate across all possible values of your random variable, it will always integrate to 1 or sum to 1. That's a probability. Your probability density function will integrate to 1. Your probability mass function will sum to 1. Okay. Likelihoods use the same probability function to get your likelihood. However, when we talk about the likelihood, this time, so when you talk about probabilities, the parameters of the model are fixed, and the variable that you kind of change and mess around with is the random variable itself. Okay? With likelihood, it's the same function, except this time the observed values, the x values, your observations are fixed, and the things that you're messing around with are the parameters of the model. And so if you, I guess the difference here is that if you integrate across all possible values of your parameter, or sum across all possible values of your parameter, it does not integrate or add up to 1. Okay. Whereas for probability, you're using the same function, you keep your parameters fixed, and if you integrate or sum across all possible values of x, it always integrates to 1 or sums to 1. Okay, I don't know. Nobody responded, so that's why I went through that explanation. But that's you're using the same function, but it's basically what do you treat as fixed and what are you varying? In probability, the random variable varies and the parameters are fixed. In a likelihood, it's pretty much the same function, but it's the values are fixed and you're messing with the parameters. Okay, so I guess this is a quick review of maximum likelihood estimation. So probability function of observing some value given some parameters theta is this. So we have the probability function x given a parameter value theta. And so the example I always like to use is, let's pretend we have a pouch and we have 10 marbles in the pouch. 3 of those marbles are red and the rest are blue, and therefore this has a Bernoulli distribution, and the probability of drawing a red marble is 0.3. And the way we would model this would be theta to the x times 1 minus theta to the 1 minus x, where x is either going to be a 1 if it's red or 0 if it's blue. Okay, and so the probability of getting a 1 is going to be 0.3, and the probability of getting a 0, if you use this, is going to be 0.7. Okay, and the other kind of key thing is that if you have a bunch of independent events, the probability of the joint probability there is going to be the product. Okay, so this is all review. So again, we have the same pouch. 3 of those marbles are red and the rest are blue. And I ask, what's the probability of drawing the sequence red followed by blue with replacement? And so, this is a very simple, intro stats 10 question. You just do 0.3 times 0.3 times 0.7, right? And that's what we get. But more formally is you say it is the product of all of these probabilities, and therefore when you put in your PMF here, you're going to get 0.3 raised to the 1 times 0.0 to the 0.7 to the 0 and whatever, and then the product of all of these ends up being 0.3 times 0.3 times 0.7. Okay. This is for this exact sequence. A lot of times Bernoulli and binomial are presented almost not the same, but they're very, very similar. And the key difference is that in a binomial, the order doesn't matter. So now you would say, okay, well, how many arrangements are there for 2 reds and 1 blue? And there's 3 arrangements, and it would be, 3 times this. But anyway, this is for this exact sequence of red followed by blue. Okay. All right, here, this is the slide that says probability versus likelihood. They both describe probabilities. The distinction is this: in a probability function is a function on the outcome x, and therefore we leave the parameters theta as fixed and we change the outcome. Probability functions must sum to 1 or integrate to 1. Okay, and a likelihood function is a function of the parameter theta. We leave the observed data x as fixed and we change the parameter theta. And then a likelihood function doesn't need to sum or integrate to 1. Okay, over all the different possible values of theta. All right, so with the likelihood function, we can do the same kind of thing. This time, however, we have a pouch of marbles, but rather than saying this pouch of marbles is 30% red, we say the proportion that it's red is unknown to us. Okay, and we draw some marbles, we get a sequence, we say we get red, red, blue. That's the sequence of marbles we observe. Again, red is 1, blue is 0. And therefore, our likelihood function, because theta is unknown to us, the likelihood function for this sequence of data is going to become theta squared times 1 minus theta. Okay. And now we say, okay, well, what is the value of theta? Okay, what is the value of this unknown parameter that's going to maximize the likelihood of this exact data? Okay, and so this question of maximum likelihood can only be answered once you have observed data. There's no such thing as maximum likelihood estimation if you don't actually have data observed, okay? So we have the data observed, it's red, red, blue, and this is our function. And then so we say, okay, now it's just a matter of maximizing this. What value of theta is going to maximize this thing? And so this is just calculus, all right? And so basically you're going to say, all right, let's take the derivative of this thing, set it equal to 0, and solve. Taking the derivative of a product is a little bit trickier, so one of the things we'd like to do is we switch everything into logs, and basically the product becomes a sum, and it's a lot easier to take the derivative of a sum, and so that's what we do. So if I take the log of this, theta squared times 1 minus theta, the log of that becomes 2 log theta plus log 1 minus theta. And because the log function is monotonic, the values that maximize the log likelihood will be the exact same values that maximize the actual likelihood. So anyway, we're going to maximize the log likelihood. We've taken the log. Now to maximize, you take the derivative, you set it equal to 0, you solve to get your critical points, and anyway, this is what we do. So the derivative of 2 log theta times log 1 minus theta is 2 over theta plus 1 over 1 minus theta times negative 1. That's because of the chain rule. And then solving for theta, you get 1 over 1 minus theta is equal to 2 over theta. Then you get 3 theta is equal to 2, and therefore theta is equal to 2/3. This is the value of theta that gives us a derivative equal to 0, where the derivative is equal to 0 will correspond to a local max or local min, or saddle point, I guess. And therefore, and this, if we do the second derivative anyway, it corresponds to a local max, okay? And in our case, a global max. And so this is the value that's going to maximize the likelihood, our likelihood function, which is theta squared 1 minus theta. Okay, so that's all review as far as maximum likelihood estimation goes. And so if we're doing linear regression, we said in our generative model, we said the actual values of t come from a normal distribution centered at w times x, okay, w transpose x, with variance sigma squared. So it's normally distributed around here. We're going to assume all of our observations are independent of each other, okay? And if that's the case, then the total likelihood of our entire data is going to be the product, okay, the product of everything. And so here I've got basically the product of all of this, and this is supposed to represent the PDF, okay, the PDF of our data. Okay, and here's our normal PDF, okay, 1 over root 2 sigma squared. Kind of the key is you're looking for an e to the negative something squared, okay? So anytime you see e to the negative something squared, it's going to have the shape of a normal-ish distribution, but just, this is just a constant. This is constant over here. But anyway, we got, this is our normal PDF. And so we're going to plug that in, and we want to maximize it, okay? So if we assume all of our observations are independent, and we assume our errors are normally distributed, the likelihood of our data, okay, given our actual values of t, given our, our predictor values x, okay? Remember, what we're trying to do is we're trying to find the values of w that will maximize the likelihood, okay? And so our total likelihood is the product of all of these normal PDFs, okay? We have a normal PDF, and we plug in, our nth observation, and we have an actual t, and we have this thing over here, our prediction, okay? And we want to find the values of w that will maximize this entire thing. Okay, so at the start, minimizing a cost function and maximizing a likelihood, we have different objectives here. Okay, so here we're trying to maximize the likelihood. Okay, all right. So this is the key here is to remember that our likelihood function, we are treating the observed values of t as fixed and our input values x as fixed, and the value sigma is a constant. Okay, and the only thing that we can actually vary and mess around with are the parameters or the weights inside our vector w. Okay, and so that's, we have a whole bunch of variables here, but the only thing that actually are variables are the w. Okay, everything else is fixed. Okay, the t's and the x are fixed values. They come directly from our data, so we can only maximize the likelihood function once you have observed data. Sigma squared is a constant. Okay, and so we want to find the values of w that will maximize this function. So just like before, we will take the log of the likelihood function to turn the product into a sum to make our lives easier, and then we're going to take the derivative of the whole thing, set it equal to 0, and solve. Okay. So anyway, if this is our likelihood, which is a product, the log likelihood, so we take the log of everything, the product becomes a sum, and now I have the log of this thing, which is log of 2 pi raised to the negative 1/2, because it's the square root of 2 pi, and then this is 1 over sigma, so that becomes minus log of sigma, and then it's log of this, of exp, the e raised to this function, and so it just becomes everything on the inside, right? The log cancels out with the exp, so this just becomes that. And then and now I'm going to distribute the summation. Okay, and so for here, because this is going to be the same for all n observations, I just multiply it by n. Okay, this is a constant for all n observations, so I just multiply by n. The only thing that actually has a subscript n and changes for each observation is going to be this component right here. And so this part, I have to kind of go through each n observation and sum them up. I can pull out the 1 over 2 sigma squared because that's a constant that doesn't vary. So so this is the only part that changes there. Okay, so this is our log likelihood, and we want to maximize this. So we're going to take the derivative of this. We're going to set it equal to 0 and solve. And so this is what we have. Okay, so I'm going to if I take the log, I get minus. Okay, so sorry. This is our log likelihood. We're going to take the derivative of this with respect to our weights w. Okay, because we want to take the derivative with respect to w. So this is a constant. There's no w there. It becomes 0. This is a constant. There's no w there. It becomes 0. And so now, what is this? Here I do chain rule. The square comes down, cancels out with the negative 1/2 over here, and I get t minus w transpose x times, and then with chain rule I take, multiply by the derivative of this with respect to w, and I get multiplied by negative x. Okay, and so with this in mind, we have x over n. Okay, the negative over here cancels out over here. X over n, sorry, not x, x subscript n. This is a 2 by 1, assuming our values are, it's just a 1 and a thing, but I mean, you could change this to whatever dimensions x are. So if you have 3 predictor variables or 4 predictor variables, you could change that. But here I just said it's a 2 by 1. Our predicted, the actual value is a scalar over here, and our predicted value is a scalar over here. So that's fine. Okay. I guess I copied this line. And so anyway, I'm going to distribute the x sub n, okay? And so this, I get x sub n times t sub n and negative minus x sub n times x sub n transpose w, okay? So this whole thing is 2 by 1. And what I'm going to do is I want to kind of switch into matrix notation. So keeping in mind the nth observation in x is just going to be 1 and xn. Okay, and again, this can be expanded if you have multiple predictors. But our big matrix X is basically consists of rows where we've just taken each x sub n and transposed it. Okay, so we have 1 x1 and 1 x2 and so on and so forth. Okay, so this is our big matrix X. Our vector t, or is just a column vector of our actual values, and our vector w of weights is a column vector of our weights. And again, these can be expanded. W and x can be expanded. We could add more columns in x. We could add more weights in w. But basically, we could say if I want to just take each the summation of xn times tn, that is equivalent to just taking big X transpose times t. Okay, so xn tn, if I say this is a 2 by 1 and we're going to sum it across all n things, you can see this is just the result of taking x times t and then just taking the whole thing, right? So if I do x transpose times t, we're going to get exactly this. Okay, and then same thing over here. If I look at xn transpose times w, this is a 2 by 1 and this is a 1 by 2, and w is a 2 by 1. So this whole result is going to be 2 by 1. Okay, and again, right now we're just kind of taking, for when I have the summation sign here, we're just taking the nth row, okay, the nth row here and nth row and multiplying it by w. But I would get the same result if I take the full matrix of x, okay, and I do x transpose x, okay. And so it feels a little bit strange, but we go from doing xn transpose to big X transpose x. But again, this is going to be, the summation of basically each of these things. So if you, for each xn and xn transpose here, you get like a little 2 by 2 for each row, okay? And if you sum that up across all n rows, it's exactly equivalent to having big X transpose x, okay? So this is 2 by n times an n by 2. This is a 2 by 2. We multiply it by our matrix W here. And so anyway, this whole summation thing here, okay, this thing with the summation here and the summation there, can be simplified. We can get rid of the summations, use the convenience of matrix notation, and have big X transpose T minus big X transpose X times W. And this is our log likelihood. Okay, the derivative of our log likelihood with respect to W. Okay, so at this point we say, all right, we want to set this equal to 0 and solve for W. So that's what we do. So we set this equal to 0 and we solve for W, and we can see that I could multiply through by sigma squared, add X transpose X W, and then multiply both sides by X transpose X inverse. And we would see the value of W that maximizes this, or the value of W so that our derivative is equal to 0 and therefore maximizes it, will be X transpose X inverse X transpose T. Okay, and this is the exact same solution that we arrived at when we said we want to just minimize the sum of squared errors. Okay, so we have two paths that arrive at the same solution. Right? The path that we looked at in the kind of first part of the course was we are trying to minimize a loss function. Our loss function is the sum of squared error or mean squared error, and we said we want to minimize it And when we did that, we got X transpose X inverse X transpose T. Here we have a probabilistic model, and we said if our error terms are normally distributed around our predicted values, which are found by doing XW, okay? And there, if you want to maximize the likelihood of your data, okay, the W's that you're going to want to select will be exactly the same, X transpose X inverse X transpose T, okay? So minimizing the squared loss is equivalent to maximizing the likelihood if the errors are assumed to come from a normal distribution, okay? Interestingly enough, that variance term, sigma squared, doesn't appear in the solution at all, okay? There's no sigma squared. And so whether your noise is huge or small, okay, as long as the noise is normally distributed, okay, and you have kind of this constant noise throughout the entire data set and observation, it doesn't affect the W that you choose. It doesn't affect your parameters that will, your slope and intercept parameters. Okay. If we inspect, here we can inspect the likelihood function, and we get some insight as far as why maximizing the likelihood is the same as minimizing the sum of squared errors, okay? And so here was our likelihood function. We said we want to maximize this, right? We want to find the W's that are going to maximize this likelihood function. And when we take the log of all of this, okay, we get the, these things turn into constants. And here we have a negative constant, okay? And this part, when you take the log, okay, it turns into a summation of basically this part right here, our actuals minus our predicted value. And so this part right here, this is the sum of squared errors, okay? So this just shows up when you take the log of the likelihood function. You basically have the expression for the sum of squared errors in here. And it's preceded by a negative constant, okay? And so if we're going to say we want to maximize the log likelihood here, okay? Maximizing the log likelihood, given that this is a constant, just means we're going to try to minimize this component over here. We're going to try to minimize this, and that's going to be exactly equivalent to minimizing the sum of squared errors, all right? And again, this only works because we have a normal distribution. This is the PDF of the normal distribution has this e raised to the tn minus basically our predicted values. Okay, e raised to the actual minus the predicted. And because of that, when you say I want to maximize this thing, it becomes equivalent to minimizing the sum of squared errors. Okay, and that's why when you do linear regression and you're using this probabilistic model, then you have to go back and you have to say, are my assumptions valid? And you have to go and you have to check your residuals and make sure that they look like they're normally distributed. You have to check and make sure that it looks like the variance is constant throughout the thing, because if that is not the case, then your likelihood function doesn't look like this, right? It doesn't follow a normal distribution. Okay. That's to check if your model is, quote, valid. But again, if you're only caring about the performance of your predictions and you don't care if your model is actually valid or not, then you don't have to bother with any of this stuff, okay? So if you're just saying, hey, I'm not actually looking for the correct model, I just want to minimize my errors, then then that's fine. Minimizing the errors is fine as well. But yeah, I mean, so I think this is also covered in 100C, where you look at kind of, these linear models and stuff like that. But anyway, so this is a review. If you've taken 100C, this is all review, and if you haven't, maybe you'll see it again. But then I want to tie it in to kind of our bias variance trade-off in our next lecture, and see how we get variance in our parameter estimates and things like that. Okay, so we'll wrap things up here for today. Just doing a review of maximum likelihood estimation. Let me give you I think I have to give you your last two view quiz answers. Last two view quiz answers today will be B as in bear, and A as in apple. Okay, so B and A. Okay, so we'll wrap things up here, and we'll see you on Wednesday.